Lecture 76, fictitious forces. What are fictitious forces? Well, you've probably experienced them if you've ever been to ride the teacup ride at Disney, where you sit in the teacup and you spin it around and around faster and faster and faster, right? And you feel like your body is going to be thrown outside of the teacup. Familiar with that? Yeah, probably done that.
What do you mean? How's the ride go? You just spin in circles?
Yeah, you sit inside this teacup, you've got this little wheel that you can grab hold of and you can start spinning it, and you can spin yourself by that wheel, you see?
So what are you saying is just like being swung around?
Yeah, exactly.
Okay.
So what is this force called? We call this the centrifugal force, right? Contrast that with centripetal. Centripetal means like center seeking or towards the center. Centrifugal means away from the center, okay? And it's interesting that Newton originally, when he derived the equation for angular acceleration, the v squared over r derivation that he did, he originally considered the forces as being outward directed forces or centrifugal forces. It was only later, I think, from the influence of Robert Hooke, that he changed his perspective and switched over to inward directed forces. But that's what we're going to talk about today. Recall that Newton's laws only apply in inertial reference frames. Those are reference frames that are not accelerating, okay? But we can actually use Newton's equations in non-inertial reference frames if we include these fictitious forces. And so I'm going to show you how that works now. All right, here's our old friend, the railway car. And on the railway car, we'll assume that this railway car is actually accelerating, some acceleration a naught, okay? Doesn't matter, but we'll say that it's a uniform acceleration. And at some moment in time, there's a ball suspended from the roof of this rail car that drops. Now our observer here on the ground, what's he going to see? Well, he's going to see the ball drop and fall straight down, right? And Newton's laws apply here. The sum of the forces are equal to m minus mg, right? So pretty straightforward problem, right? So we could describe the position if we allow this to be, for example, the y-axis, right? We could say that the ball starts out at some position y naught, right? And then it will accelerate downwards with the acceleration g. And so you might recall that the equation for the position, the y position as a function of time, will be y naught minus 1/2 gt squared, right? Because gravity is a uniform acceleration, okay? That's fine, but what about someone on the rail car itself, right? What would they see? Let's look at that. If we can, like this, let's put this person standing right underneath the ball, right? That's dangerous, right? Here's where the ball was initially, and after it drops, because the train is accelerating, right? Don't forget that. The ball is going to wind up over here, okay? And how can the guy on the train explain this, right? From his perspective, it's as if there was a force acting on the ball, not just bringing it down towards his head, but a benevolent force that was also moving it away from his head to the, I guess, his left or right, I don't know which way he's facing, right? So we've got the usual minus mg, let me just draw it a little bit bigger. This is the ball initially, we'd have minus mg going this way, but we also have, I want to do a vector addition, so I'm going to draw it head to tail. We also have this force, or a fictitious force, rather, minus m times a naught, I called it, right? A naught. Let me draw it a little nicer. Minus m a naught. Okay? Notice it's in the opposite direction of the actual acceleration of the train, but from the guy on the train's perspective, it's as if there was some strange force pulling the ball to the back of the car. That's how we'll say it, the back of the car, right? Does that make sense?
Yeah.
Just imagine being in an automobile that's undergoing acceleration. So you've got the pedal to the metal, as they say, and if you were to throw a ball up in the air just as you hit the accelerator, the ball would accelerate towards the back of the car. Or conversely, if you were to hit the brakes, that's an acceleration in the opposite direction, right? Everything in the car would go flying forward, as if some mysterious force, right, threw it into the windshield, right?
So it has to be accelerating, the car.
The car has to be accelerating, exactly. If the car is traveling at a constant velocity, right, then we're talking about an inertial reference frame, right? Then we would just have a relative velocity between our observer on the track and our observer. So here's our observer on the track, and here he is at this later time here, right? He's right on the same position as the ball. right? So from his perspective, the train car is accelerated to the right, okay? But accelerated. Now remember, when we did special relativity, we only considered trains that were moving at a constant velocity, okay? So both frames were inertial reference frames, okay? Here, we are not in that situation. The train is definitely a non-inertial reference frame. This person standing here, he will also experience a force, a fictitious force, rather, as if he was being pulled to the back of the car. We'll assume he's standing in a good sturdy stance, and so he's not going to go anywhere. But the ball doesn't hit him on the head, right? It actually goes off this way because of the acceleration. If I were to try to use Newton's laws in this reference frame, we'll call it the primed frame like we usually do, right? We say the sum of the forces in this primed reference frame minus mg minus ma naught. Okay, so this is, of course, just the gravitational force. Gravitational. This, however, is a fictitious force, so we'll just call it fic force. They don't actually have a name for this fictitious force. This is just the stuff goes, flying in the car when you slam on the brakes, right? Force. But it's not a real force, right? That's something that's important to note. In the next lecture, we're going to be talking about general relativity, and it will be an important distinction that, right, if you can undergo a coordinate transformation and get rid of this fictitious force, like going to the observer frame here, for example, right, then you can distinguish between a real force and just an accelerated reference frame. It's when you can't find a coordinate transformation which does that for you, that you have a real force on your hands, okay? Let's talk about a well-known force that we talked about at the beginning of the lecture, the centrifugal force. So for that, I'll have to draw a picture. Okay, here I've got a little carousel, okay? And it's got a post at the center of it. It's a rotating carousel. It's rotating in the counterclockwise direction. And it's got a little box of mass, right, tethered to a post at the center of this thing, right? And so this is a line run from the box to the center point, right, where it's tied off. And so there'll be a tension in that line, right? And you might recall that the force, the tension, right, will be the centripetal force, right? So from the point of view of this observer here, right, this box will be spinning around and around and around, right? And it's going to be held in that circular motion, right, by a centripetal force, okay? And then remember that's just the v squared over r, right? So mass times v squared over v. Yeah, v squared over r, sorry. But what about to an observer that's actually on this thing? I'll make him a solid-headed guy. So an observer on the platform that's rotating with it, right? He will see a tension in the line, but right, nothing is moving relative to him, right? This box is just sitting still, okay? Because he is rotating around just as the box is, right? But there's still a tension in that line, right? And so his explanation for the tension in that line, right, is that there's a force pulling outward, right? We'll call this force F centrifugal, maybe CG, centrifugal, right? F sub CG, and this fictitious force F sub CG is going to be equal to the mass times the velocity v squared over r, okay? So this is the centrifugal force that we talked about earlier. And if he were to write Newton's equations down, right, he would have to write that the sum of the forces was equal to, you have to include this centrifugal force in it, okay? And so he would get a mass times acceleration is equal to mv squared over r, okay? So in order to use Newton's laws in this non-inertial reference frame, it's non-inertial because it's accelerating. The acceleration is this circular acceleration, right? It's always changing direction, yes? He would have to include the centrifugal force in order to work out problems, right, in this reference frame. Okay? I think that's pretty straightforward. It's often misused, right? Sometimes people will say things like, the centripetal force is balancing out the centrifugal force of a satellite, and that's why it's orbiting. And that's nonsense. That's not the correct explanation. The centrifugal force is a force that only exists in a non-inertial reference frame. Okay? It's not a real force. It's fictitious, but it's what we have to do to account for the fact that we are accelerating. Okay? The person on the ground observing this would only account for one force, and it's a real force, and that would be the centripetal force, and that is the force that's pulling this object towards the center point, right? It's always accelerating it towards the center point, you see? That's what's keeping it moving in a circular position. You can imagine if you cut this line at any point in time, right, that whatever the velocity was, let's assume this is a perfectly circular orbit, the velocity would be in this direction, right? And the box would just fly off in this direction, right? Yes? Because it's just going to continue going like it always has gone, okay? And one of the characteristics of an inertial reference frame is that objects that aren't experiencing any forces, any net forces, right, travel in straight lines. And that's exactly what it would do were we to cut this string, okay? But it's traveling a curved path because it's experiencing a centripetal force. Does that make sense? It's a little bit of language that you use. But I mean, you can imagine being out here. You'd be like, well, what is it that's pulling this thing out, making this line tight? If you're standing on this merry-go-round or carousel or whatever you call it, right, you would feel this line to be tight, right? It would feel like stuff was being flung outward, right? Radially outward, okay? Just like in the teacup, okay? But it's a fictitious force, okay? There's one other force I want to talk about, and that is the Coriolis force. Okay, here we have a carousel again, okay? We've got a person standing at the center of the carousel, and he is going to throw a ball in the radial direction, in a radial direction, outward, from the center, okay? And we have an observer who's not in the rotating reference frame, standing here, okay? So here the guy throws the ball. He's thrown it to this guy who's on the circumference of this merry-go-round, okay? And then sometime later, the inertial observer, of course, is going to see the ball travel in a straight line because the guy threw the ball with a constant velocity, and there are no forces, we'll assume, acting on the ball in any way, and so it's just going to travel in a straight line to this point right here. But in that time, the person that was located here originally, that the ball was thrown to, well, he's rotated around by some angle, and I'll indicate that angle here, right? So he's moved some angle theta, okay, in the time that the ball was thrown, and of course the ball misses, okay? Now I understand you guys did a experiment like this in Germany. You had some kind of a merry-go-round where you could throw balls at each other and miss, right? Okay. The same concept here, right? You throw the ball towards the guy, you're looking at him, you throw it in a straight line, and then you miss, right? Now to the person on the ground, everything looks normal, right? He's like, well, he threw a ball in a straight line, it traveled in a straight line, right? This is the straight line that traveled, right there, right? You see the straight line that the ball traveled? It's this one right here. Yes? What does it look like from an observer on board the platform? How would he see it, okay? So let me just see if I can draw it like this. So on board the platform, of course, the guy at the center and the guy who was originally about here, right? They don't move. They don't see themselves moving, of course. We're not going to worry about the person on the, not on the, do they call it a platform? Platform is usually the inertial reference frame. Person on the merry-go-round. So I'm drawing this from the perspective of the people on the merry-go-round. So I'll put an observer here on the merry-go-round, right? Well, we have to map what this would have looked like to this guy here, right? He sees himself as still straight across from him, but he sees the ball. It appears that it is to his left, right? So if I'm that guy, it's like, hey, throw it to me the ball, but it was over here, right? So what does the ball path look like to him? It looks like this. Traveled some curved path, you see? Now, we can actually, this, by the way, is an effect called the Coriolis force, okay? It's because at different distances from the center, you're moving at a different velocity, right? Because remember, the velocity at any given point, right, is proportional to the distance from the center, okay? Let me just write this stuff here. Okay, let's see if we can calculate the acceleration, this Coriolis acceleration. So, we've got this rotational angle omega, right? And omega is defined as delta theta over delta t. Here's our delta theta here. I just wrote this theta to get the idea, right? So that's how fast this thing is rotating, okay? But we also have this arc length s, right? So that's the distance at a point here on the circumference of this travels during this same time interval, right? So we can have s is equal to r theta. So if I do a delta s over delta t, right, this will be delta theta over delta t, okay? Now the ball is thrown with some velocity v, right? And so the velocity v of the ball is going to just be equal to, the distance that it travels is r, because we've thrown it from the center to the circumference, and that's a distance of r. And so that'll be equal to the velocity times the time, okay? So we need to use all of these things. So let's see if we can write an equation for s, the distance that it travels from here to here, r theta, but that's going to be theta we can get from omega times t, right? So we think of this as all deltas, right? And omega is theta over t, so theta is equal to omega times t. So we can replace this with omega times t. Okay? We can replace r, however, with vt. So this is equal to vt times omega times t, right? That's going to give us v omega t squared, yes? And then for reasons, remember that when we write for a constant acceleration, we like to write the distance traveled is 1/2 times the uniform acceleration times the time squared, right? So I'm going to try to write this in that form. S equals 1/2. Since I don't have a 2 in here, I'm going to put it in, right? So since I don't have a 1/2 in here, I have to put a 2 in here. So 2 omega v times t squared, okay? See, the 2's just cancel whenever I multiply through. We'll call this A sub cor for Coriolis acceleration, right, is equal to 2 omega times v. Okay, so it's a velocity-dependent acceleration that you would witness in the rotating reference frame. Okay, the faster you throw it, the more profound this effect is. Okay, and so now if we were to write this as a force, right? Forces are mass times acceleration, so we could also write the Coriolis force, which is a fictitious force, right, that we would use if we wanted to apply Newton's laws in this rotating reference frame, right, is just equal to the mass. Well, I guess we want to do it like this. Be 2 times the mass times omega times v. I think that is correct. Okay? So that's the Coriolis force. This actually has an effect, okay? If we think of a globe, right, let me see if I can draw a little picture of that. Maybe over here. Get rid of this for just a minute. Do my best to draw a globe. And let us imagine that we throw a ball. So I'll imagine some inertial, outside inertial reference frame, right? The Earth is going to rotate in this direction, right? Because the sun rises in the east. This is the North Pole, so north, east, south, west. There's our compass rose, right? If we imagine that a ball is shot towards the equator in both directions, okay, like this. And imagine that there's a person there that's going to catch these two balls, okay? But the thing is that because the Earth is rotated sometime later, right, he won't be there anymore. He'll be over here, right? And so the effect of that is that from his perspective, if you put yourself on the Earth, right, in this rotating reference frame, and what it's going to look like instead, oh, that's a terrible circle. What it's going to look like instead, draw a little equator. Of course, you'll think you're still here, right? You're going to see this ball thrown, and it's always, you're standing, it's to your left, right? So it looks like this one curved like this, and it looks like this one curved like, they should meet at the same point though, right? Because they landed here together, right? Like this, you see? So from the perspective of the guy standing here on the equator, right, he sees that they curve this way, right? And so it is this Coriolis effect that's at play here, right? And it's a force which is always, to the right of your velocity vector, if you want to think of it that way, right? In the northern hemisphere, and it would be to the left of your velocity vector in the southern hemisphere, okay? And this is the reason behind the rotation for hurricanes, right? So if I were to not a meteorologist, but the basic idea is as follows. If we imagine a low pressure point, low pressure zone, right? That's where the pressure is low. So what happens when you have a low pressure zone? Well, wind emerges, right? So air will rush in towards this center point here, right, in all directions. Yes? Okay? But if we put ourselves inside the northern hemisphere, right, because of the Coriolis force, instead of traveling straight towards the center, what ends up happening is these forces curve off like this. Let me see if I can get rid of these old lines. And this ends up giving you this counterclockwise cyclonic action up in the northern hemisphere. In the southern hemisphere, it'd be exactly the opposite. You'd have a low pressure, so we'll call this north, south. In this case, curve the other way, and so you get a clockwise rotating hurricane or typhoon, whatever it is they call them down there. And so that's the reason why, though. It's because of the Coriolis force. Do you guys understand? It was a little fast. But just to summarize, right, fictitious forces, right, why are they useful? Well, they're useful because in a non-inertial reference frame, if you want to apply Newton's laws, then you can only do so if you incorporate these fictitious forces into your equations, right? So you can use Newton's laws as long as you incorporate these fictitious forces into the equations that you're trying to solve, okay? Does that make sense?
Yeah.
Yeah. So they're going to be important to us in the next lecture when we start to talk about general relativity and the equivalence principle, okay?